Let us learn about relations on sets. In this video, I have defined what is a relation. I have explained some very important types of relations with an example each, and then I have winded this with one or two problems on the same concept. Let me begin with the definition. A relation R on a set A is a subset of the product set A cross A, which is the set of all ordered pairs A comma B where A and B are any two elements of A. So a relation could be any subset of this product set A cross A. Or in simple words, we are trying to relate any two elements of a given set A. If an element A is related to an element B under a given relation R, we use the notation ARB to represent the fact that A is related to B under the given relation R. There are various types of relations one can think of or which you have come across in any basic course in algebra. But I have taken here four main types which are usually considered when it comes to solving problems. First one is a reflexive relation, then comes a symmetric relation, then there is something called an antisymmetric relation, and the other one is a transitive relation. Let us look at each of these one by one with an example each. What is a reflexive relation? If A is a given set, then for every element A in A, if A are A, that is, every element of the given set is related to itself under the given relation, then you call such a relation to be reflexive. Example, consider the set of all natural numbers, that is, the set consisting of positive integers 1, 2, 3, and so on. And here you define A or B if and only if A divides B. To say that if I take the numbers 2 and 10, we know that 2 divides 10, therefore under this relation 2 is related to 10. Whereas if I take 2 and 5, we know that 2 doesn't divide 5, therefore 2 is not related to 5. So when we consider this example, we see that any number divides itself and it makes it a reflexive relation. Therefore, this is an example of a relation which is reflexive. Coming to what is a symmetric relation. As before, if A is a given set, for any two elements A and B in A related to B must imply B is related to A. Whenever this happens for every pair of elements of A, you call such a relation on A to be symmetric. Example, on the set of all integers, if you define A or B if and only if A into B is even, this gives you an example of a symmetric relation because whenever A into B is even, we know that B into A being the same value is even. So A or B will always imply B or A. An antisymmetric relation. For every pair of elements A and B in a given set A related to B and B related to A must imply A and B are the same. So this is what is called an antisymmetric relation. So you take any two elements from the given set. Whenever both the way relations exist between those two elements, they cannot be different. They must be representing the same element. Then such a relation is said to be antisymmetric. Let me take an example now. On the set of all real numbers, define A or B if and only if A is less than or equal to B. The natural ordering of numbers we have considered here. Now, if you take any two real numbers A and B, and if I assume that A is less than or equal to B as well as B is less than or equal to A simultaneously, the only choice we are left out is with A and B must be the same. Because we know that if two numbers are distinct, they cannot satisfy both the way inequalities. It cannot happen that A less than B and B less than A holds at the same time. So it can happen only when A and B are the same. So this is an example of an antisymmetric relation. Coming to what is a transitive relation. In this case, if I take a relation R on a set A, for any three elements A, B, C in A, whenever A is related to B and B is related to C, it must imply A is related to C. So first element related to the second one and the second one related to the third, then the first one must be related to the third, then you call it as a transitive relation. Example, on the set of all real numbers, define A or B if and only if A is strictly less than B. Nothing special about strict inequality. I could have as well taken less than or equal to, which would also work. Now here I have taken A less than B. Now if I take any three elements A, B, C from the set of real numbers, and if I assume that A is less than B and B is less than C, then it will imply A is also less than C. Therefore, the strict inequality on the set of real numbers is a transitive relation. You should also be careful that if I go into the case of complex numbers, this won't give you any relation as such, because in the set of complex numbers there is no order. But here I have taken the domain to be the set of all real numbers. Now, what is an equivalence relation? A relation which is reflexive, symmetric, and transitive is called an equivalence relation. So the three of the previous types of relations that we have defined, that is reflexivity, symmetry, and transitivity, a relation which satisfies all these three conditions is called as an equivalence relation. We should look into a problem now. Verify whether the following is an equivalence relation. The relation given here is for all a, b in z, that is set of all integers, define a or b if and only if modulus of a minus b is strictly less than 2. Modulus of a minus b stands for the distance between two numbers on the real line. You can also check this problem by changing the domain from integers to the real numbers, whereas here I have taken it to be the set of integers. Now, to check whether it is an equivalence relation, I should check whether it is reflexive, whether it is symmetric, and whether it is transitive. We shall first see whether it is reflexive. Now, if you take any integer, what is modulus of a minus a? It's always 0. And 0 is strictly less than 2. Therefore, any element a is related to itself under this relation, which makes the given relation to be reflexive. Now, if I take any two integers a and b, we know that modulus of a minus b and modulus of b minus a is the same. Therefore, if modulus of a minus b is strictly less than 2, then modulus of b minus a will also be less than 2. So we get R is symmetric. Let us come to transitivity. Now, if you take three numbers, for example, I have taken here a equal to 3, b equal to 4, and c equal to 5. We know that the distance between 3 and 4 and the distance between 4 and 5 on the real line is 1. But whereas if I consider the distance between 3 and 5, it is 2. And we see that because the distance between 3, 4 and 4, 5 are 1, both the values are less than 2. So 3 is related to 4 and 4 is related to 5 under the given relation. But this distance is not less than 2, it is equal to 2. So 3 is not related to 5 under the given relation. That says the given relation is not transitive. Here 3 is related to 4, 4 is related to 5, but still 3 and 5 are not related. Therefore, the given relation is not transitive. So what's the conclusion? It is reflexive, it is symmetric, but still it is not transitive. Hence, the given relation is not an equivalence relation. Let us look at one more. Again, I have taken the domain to be set of all integers. Here we will define a related to b if and only if modulus of a square minus b square is equal to 0. Is this reflexive? Yes. Why? Because modulus of a square minus a square, that gives you modulus of 0, which is 0, and this is true for all the integers. Therefore, R is reflexive. Is it symmetric? Again, the answer is yes, because modulus of a square minus b square and modulus of b square minus a square, distance between two numbers, whatever their order is, the distance is always the same value. So if one of the value is 0, the other one will also be 0, which makes R symmetric. Is it transitive? Yes, this is also true because if I take three integers a, b, c now, modulus of, and if I assume a square minus b square modulus value is 0 and modulus of b square minus c square is also 0, then if I start with modulus of a square minus c square, I can subtract and add b square here inside the modulus, and modulus of the sum of two numbers is always less than or equal to the sum of the modulus. Triangle inequality you call it as. So I get this value is less than or equal to modulus of a square minus b square plus modulus of b square minus c square. Both these values are 0, and left hand side being modulus value, the least value modulus or the distance can take is 0. So if I'm saying it is less than or equal to 0, it has to be equal to 0 as well. So we get if A is related to B and B is related to C, then A is also related to C. So this is an example of an equivalence relation. So the given relation is an equivalence relation. What was the relation here? ARB if and only if modulus of a square minus b square is equal to 0. Let me give you this problem. Or before that, let me ask this question. The previous relation which we were talking about, that is a related to b if and only if modulus of a square minus b square equal to 0, is it antisymmetric? Though this verification is not required to answer the previous question, that is we were checking whether it is equivalence. To be an equivalence relation, it has to be reflexive, symmetric and transitive. That's all. But let us go for this check whether it is antisymmetric. The answer is no here because, let me take an example here. I'll take 3 and minus 3. We know that modulus of 3 square minus 3 square, 3 and minus 3 have the same square value, that is 9. So this value is 0. And minus 3 square minus 3 square is also 0, which says 3 is related to minus 3 and minus 3 is also related to 3. But they are not the same. What do you mean by antisymmetry? If A is related to B and B is related to A, they must be the same. But here you have two different numbers satisfying both the way relations. Therefore, this is not antisymmetric. Though it is an equivalence relation, it is not antisymmetric. Now, this is a question for you to work out. For all natural numbers, n is the set of all natural numbers here. So you define on the set of all natural numbers A related to B if and only if A divides B. And the reflexivity also had taken this division as an example of reflexivity, but here the work is on the set of natural numbers, check whether this relation is an equivalence relation. So you need to check whether it is reflexive, symmetric and transitive. That is on the set of natural numbers. Once that work is done, you can change the domain from natural numbers to the set of integers and check whether on the set of integers this defines an equivalence relation. Okay, so please do this work and let me know the answer in the comment box. Thank you.